Hi, this is Mathias Trabs from the University of Hamburg. I would like to talk about the joint work with my PhD student Florian Hildebrand on the parameter estimation for stochastic PDEs based on discrete observations in time and space. What we are going to consider in this talk is the easiest SPE that you can imagine, so it's the stochastic heat equation on the unit interval in one spatial dimension. So the time derivative is given by the second space derivative, and we have a random forcing which corresponds to space-time white noise. Here writing it this way, this bt is a cylindrical body motion, and we have two unknown parameters. We have the diffusivity parameter theta and the volatility parameter sigma. We consider Dirichlet boundary conditions and some random initial condition. Here in this image you see a trajectory with an initial condition given by a parabola. Throughout the talk we consider an initial condition such that the solution field here is stationary, which simplifies things a bit. Our aim is to estimate these two parameters based on discrete observations of this solution field here. In order to understand what we are facing, if you're not so familiar with SPDEs, you can imagine this object as an infinite dimensional SODE, and doing so we obtain this representation as an infinite factor model where we take the eigenfunctions of the Laplace operator as a coordinate system, and then in each direction we have a coordinate process small xk whose dynamics are given by an Ornstein-Uhlenbeck process. We see here again our two unknown parameters sigma and theta, but we do not observe the small xk, but this mixture here, so it's not that easy to extract information on theta and sigma from our observations. Another way to think about it is as just a centered Gaussian field. If we consider here our solution field, it's just a centered Gaussian field. So everything is encoded in the covariance structure, which I wrote here. In particular, you see that the sigma squared is just a scalar, while the theta is more difficultly hidden in the covariance structure of this object. So we consider discrete observations on a regular grid, which is illustrated here. We cut out a margin at the boundary of the spatial domain here for some technical reasons. And then inside this rectangular we have a regular grid. We have altogether n observation times and m spatial points where we observe our solution field. And as n and m goes to infinity, we end up with a high frequency regime where capital delta is the time frequency and small delta is the spatial observation frequency. What we would like to understand is the dependence of our estimation problem on the spatial and the time sampling frequencies. We would like to estimate both parameters jointly, and of course we would like to know the convergence rate. Estimation of the parameters for SPDs based on discrete observations goes back to a paper by Markussen who considered MLE, and then there are many papers considering what appears natural, namely realized quadratic variations or even more general stuff, but usually authors consider only quadratic variations along time or along space. And actually you can prove that if you just do one of these two things, you cannot estimate both parameters jointly. This is the reason why we consider space-time increments, so we take into account the complete covariance structure that we have. So what you see here is a time increment and then another time increment, and then we take difference at two successive spatial points, and you can reorder everything such that you have the difference of two successive spatial increments. And the corresponding quadratic variation is then this realized space-time quadratic variation, where we square these double increments and then we average. And here we have to be careful with the normalization. We have here a normalization factor that automatically is doing the right thing if the spatial frequency is dominating, then it scales like delta. And if the temporal frequency is dominating, then it scales like square root delta. And here you recover the regularity of the solution field. Along space, it's like Brownian motion, and along time, it's like a fractional Brownian motion of order 1/4. In a special case where this sampling ratio is a fixed constant small r, then this dependence of this normalizing factor can be simplified at first order, and the dependence on the theta can be made explicit, and this is what we will exploit then also to estimate the theta. Here we have a central limit theorem for this space-time quadratic variation, or the realized space-time quadratic variation in the two regimes where either one of the sampling frequencies is dominating, or in this balanced design the convergence rate is m times n, which is the total number of observations, and the asymptotic variance will depend on the sampling ratio. So based on that, it's not difficult to construct method of moment estimators either for sigma squared or for theta in the case where we have a balanced design. And then what we see here in this picture is the robustness with respect to the sampling frequencies that we would like to have. On the x-axis you have the logarithm of square root n divided by m. So here on the right hand side the temporal resolution is dominating, and you see that this black line corresponds to an estimator for sigma squared based on only temporal increments, and this works fine here, but it does not work at all where the spatial resolution is dominating. The same picture inverse you get if you consider an estimator based on spatial increments, but our double increment estimator is robust with respect to the sampling frequency. It works throughout very well, and here you have the analogous picture for estimating theta. Now what we would finally like to have is the joint estimation of sigma squared and theta, and again based on our realized space-time quadratic variation, we can construct an M estimator for both parameters jointly. And here we have a central limit theorem only in the balanced design, but the rest is as we would like to have. We have this parametric rate and some asymptotic covariance matrix, which I omit here in the slides. Now what can you do if you are not on the balanced design? Assume you have a finer resolution in space. Then what you always can do is you can do some thinning. You throw away in a way data, and you get here to the line, and this line, this parabola, is exactly the case where we have balanced design. The same can be done if we have more temporal observations. You can go down, you reduce your data, and you come here at this line. Okay. This does not look very sophisticated, but actually it works, and it gives you the best optimal weight that you can hope for. You can improve this a bit by not throwing away, but averaging then with respect to these reduced sampling frequencies. But what you obtain at the end is an estimator which does not achieve in general the parametric rate, but the rate that you see here. It's the square root of n to the 3/2 minimum m, and actually it turns out that this rate is minimax optimal. It cannot be improved up to a logarithmic factor. So what we see is that if we are in the balanced design, we have this parametric rate. And this comes from the fact that we add the same amount of information in time and in space, where the square root that you have here reflects the scale invariance of the stochastic heat equation. In general, and that's the take-home message of this talk, you don't have a parametric rate, but you have this, well, this more difficult object here. But if you write it as n minimum m squared times m minimum square root n, that's exactly the picture with the arrows I just showed on the previous slide. Thank you very much for your attention.